urban area radio wave propagation. Propagation within buildings, inside buildings, near buildings, and into penetration of buildings. First, propagation within buildings, within buildings. Okay, propagation within buildings. We have attenuation due to walls. We have walls and diffraction from obstacles, chairs, tables, screens, lamps, and so on. This is the path loss of in a building. Here, lambda is the wavelength. LE is the distance dependent loss in excess of free space loss due to diffraction. Distance dependent, the loss depends on the distance, of course, and this is in excess of a free space loss. This is the loss more than the free space, or the loss without a free space. This means that there is a free space loss, and this is the loss over and above the free space loss due to diffraction. Here, gamma n is reflection coefficient from walls or from screens, and Tm is transmission coefficient through walls and screens. Figure 7.13 shows LE. LE is the distance dependent loss in excess of free space loss due to diffraction versus distance in meter at frequency of 900 megahertz, the mobile frequency, cellular telephone frequency 900 megahertz. Omega C, this is omega C here, this is omega C, this clearance is omega C. From here to here you can see this is omega C. This is omega C is varies between 1.5 and 2 meter. Different buildings with different specifications. Office environment, this figure 713 is for office environment, and let's see figure 713. This is figure 713, excess propagation factor in an office environment. This is typical. Of course, this is typical curve. Maybe for different buildings you will get different curves, but this is an average curve. You can see here that below around 30 meters, the distance inside the building is less than 30 meters, the attenuation is insignificant, very small. You can consider it is almost zero. After 30 meters distance between a transmitter and the receiver within a building, the attenuation becomes falls fast. Here. Yes. This is summarized here. For distances less than 30 meter, the excess loss is almost 0 dB. Of course, there is free space loss plus the excess loss, which is 0. So the loss will be only free space. For distances greater than 30 meter, at 40 meter, it is minus 11.5, and at 100 meter, it's minus 49.5 dB. Let's see, 40 and 100. 40 meters, it is minus 11.5 dB, and at 100 meter, it is minus 49.5 dB. Here we want to find the exponent of power law as we learned before. Let's see, at 40 meters here, this is 30, 40, 50, this is log scale. This is the 40 meter here, this is the 40 meter, and here is the value. This is linear, this is 0, minus 10, minus 10, this is almost minus. If you use the ruler, you will find it that this is this way. You will find that this is you will find that this is 11 minus 11.5 dB. Minus. Okay. And at 100 meters, this is 100 meter here, the loss is approximately, it is very close to 50, it is minus 49.5, minus 49. Okay, let's go back here. Here we have at 40, we have seen from the figure that it was minus 11.5, and at 100 it was minus 49.5. The difference is this minus this is 38 dB difference. Now 10 log the distance 100 over 40 to the power n, the exponent power law, is equal, the difference here is 38. From this you can find that 10n, 10 and log 10 and log 100 over 40 is 10 over 4, which is 2.5. Equal equal 38 dB, and n is equal n here is equal to 38 divided by 10 log 2.5. N is equal 38 divided by 10 times 2.5 log, close bracket, and this would equal to, as you can see, 9.55. This is the exponent of power law, which means that the loss is proportional to 1 over distance to the power 9.55. It is very large slope. The loss, if you take dB, this would be minus this, so this is a large loss. The loss increases very large in a large rate with distance. As an example, assuming an office environment at 900 megahertz frequency is characterized by figure 713 that we have already seen. Find the field strength 50 meter inside the building. This is inside the building. In the field, if the field strength outside the office building is 60 dB microvolt per meter. The field outside here is 60 dB micro, and we want to find if the receiver is here. You can see this is the receiver here. It is at 50 meter away from the wall. We want to find this here. and the penetration loss is 6 dB. Well, the loss, so the signal is 60, you subtract the penetration loss 6 dB here, and so you subtract the loss at 50 meter, which is from here. The loss at 50 meters, this loss is at 50 meters, is maybe minus 21, around minus 21. The loss is around 21. So we 60 minus penetration loss 6 minus the loss here due to propagation here is 21 dB. Here is an example. Determine the exponent of power law for London model at 150, 450, 930 megahertz. Figure 710. So from the curve 710, the 1 kilometer, the LIP, the loss is minus 100 dB. At 10 kilometer, the loss is greater. It's 144 dB. So 10 log distance 10 over 1, you will subtract 144 minus 100 is 44, and you take 10n log 10, this is 10n equal 44, and n is equal 44 over 10 is 4.4, simple. And we repeat this here at 450 megahertz. At 1 kilometer it is minus 105, at 10 kilometer it's 151, and here again you have 151 minus 105, you have this 10n, this will be 10n. 10n is equal 46, then n equal 46 over 10 is 4.6. And similar thing here, we subtract and we divide by 10, so 52 by 10 is 5.2, so the loss is 4.4, 4.65. Now propagation near buildings. Okay, this model is a two-ray propagation model. There is a breakpoint where the slope has a certain value before this breakpoint and it has another value after this point, usually 20 dB before and 40 dB after. Like this, the slope might be like this, then after that it will decay faster like this. So usually this is the slope here, usually is 20 dB per decade, and here 40 dB per decade. The breakpoint here, the distance here, this the breakpoint here, this dB, d, not decibel, this is break distance, is given by this equation for h1, h2 times lambda. H1 is the transmitter height, h2 is the receiver height, and lambda is the wave length. Example, h1 is 4 meter, receiver height is the mobile telephone 1.6 meter, so, and the frequency is 1.9 gigahertz. We want to find dB. The wavelength is the speed of light divided by the frequency 1.9, giga is 10 to 9, and we have here 4 times h1 is 4, h2 is 1.6, and we calculate the value here. 4 times 4 is 16 times 1.6, this will be in the numerator times 1.9 10 to 9 divided by 3 10 to 8, and the answer would be 162 meter is the answer. For D, distances less than the breakpoint, as we said here, the slope is proportional to 1 over d squared. When you take 10 log d squared is 20 dB, as we said here. It's minus 20 dB. And when the distance is greater than a breakpoint, the slope is 1 over d to 4. 10 log this is minus 40 dB per decade. Decade means that each time you multiply distance by 10, the attenuation will increase by 40 dB. And the 20 means that if you multiply the distance by 10, the attenuation will increase by 20 dB, or the signal level will decrease by 20 dB. Okay. This is low antenna microcellular airband model, where the loss is given by this equation: L low minus 71.2 minus 52.9 log d km is the distance in kilometer minus 20 log f in megahertz, frequency in megahertz. Take this example here. A portable user of a low antenna airband 1.5 gigahertz microcellular personal communication system experiences an average range of 900 meter. What would the range be from a 100 meter high fixed site in a suburban area that can be described by the diffracting screens model? This is the model that we described at the beginning of the chapter, with the B, building height 15 meter, and separation between buildings 40 meter, and W, the distance between the building before the last building before the mobile and the mobile is 20 meter. So the mobile lies midway between two buildings. Allo, we have seen this equation here, is this minus 172. This equation here, we take this equation here, is the equation. Is the equation minus 71.2 minus 52.9 log d, and this is the equation here. It's L for low height antenna. If you put the distance, the distance is 900 meter, which is 0.9, because we have to put this in kilometer, 0.9 kilometer, and the frequency is 1.5 giga is 1500 mega. This mega, and we obtain also the here 71.2 minus 52.9 times 0.9 log minus 20 times 1500 log. It is here minus 132, as you can see, minus 132.3 dB. Now we can use the equation for the screens model to obtain the required range if we use the other model. Propagation into buildings. This means the penetration loss when the wave penetrates the walls, the outer walls of the building. Penetration loss into building decreases by 1.5 dB, by about 1.5 dB per floor with increasing floor level. This means that the ground floor has higher loss, the first floor lower loss, the higher floors has lower losses. Now we have this problem example. A pair of 915 megahertz portable, this is the frequency. This is the frequency. This is the frequency. Operating frequency. Portable radios operate at a system gain, including antennas, of 110 dB. System gain. This is total gain, including antennas. System gain. Okay. Estimate their range, the distance. We want to find the distance. Find the distance. Find the distance between them. The maximum distance within an office environment, so we can use figure 713. Now the system gain 110 dB as given here is equal to the system gain should equal the total loss. The total loss is the free space loss and the excess loss to free space. This is free space loss. This is free space loss. And this is the loss in excess of a free space. This is the extra loss after the free space. At 50 meter, you can see here, at 50 meters the loss is around minus 21 dB. Here at 50 meter it is 21 dB. After the 50 meter, as you can see here, we'll go back to the figure to show you that here you can see that after 24, after 50 meters the curve is linear, and we can use after 50 here 50 meters. After 50 meter the curve is linear. Here 50 meter it is linear, and we can use this formula here. The exponent of power law is, we have derived that, it was 9.5 here. We can use this equation here. LE is proportional to 1 over distance to the power 9.55. We can use this equation here. Yes. So this is the loss at 50 meter, and this is the loss after the 50 meter, because we assume here that the distance is greater than 50 meter. If the distance obtained is less than 50 meter, our assumption will be wrong and we have to repeat the question. If the distance obtained is greater than 50 meter, then our assumption was okay. This is the total loss in excess of free space. Now 110 minus 21 is 89, minus 10 log, this is constant, 4 pi over lambda, or we can take it because the frequency is given here. Frequency is 915 megahertz, can put here, and from 951 megahertz we can find the, so this is log 4 pi over lambda, this here 10 squared, of course we have, minus 10 log 1 over lambda squared, minus lambda, minus plus 10 log d squared, because we have here d, plus 10 log d squared here. If we take it to the other side, it will be minus, of course. So this is minus and this is minus. We take to the left side, 110 minus 121 is 89, minus 10 log 4 pi over lambda, also minus because we take this here, minus 10 log d squared, and this is here negative because this in the denominator. When we take it here, it will be positive, so plus 10 log 1 over d plus 10 log 50 to the power 9.5, 10 log 50 to the power 9.5 here. This is positive, so on the other side it will be negative, so minus 10 log d to the power 9.5 and equal 0. That's all the terms. Substitute for lambda here, 915 megahertz. We can find the wavelength to find this value here, and d is of course, this is 20 log d, and this is minus 95 log d. Minus 95 log d and minus 20 is how much? Minus 95 minus 20 is minus 115 here. 115 over 10 is 11.5 d. And this is constant, and this is constant. Okay, calculate this here. Lambda is equal C 3, and we can 4 pi, 4 times pi times lambda is equal C over F, so F will be in the numerator, times the frequency is 915 megahertz divided by the speed of light, 3 times 10 to 8 meter per second, equal, and we take the log of this and multiply by 2 times 10 is 20. The answer is 31.67. You can see here 31.67. So this is this 31.67, and 89 here is as it is, and we have added this and this. This is 20 log d, and this is 95 log d. Minus 20 log d minus 95 log d is minus 11 log d, which is minus 10 log 11.5, because 115 over 10 is 11.5. So this and this are this term here. The remaining term is this term, so this should equal to this. Let's check. 9.5 times 10 is 95 times log 50. 95 times 50 log is equal. This is 161.4, and here 161.4. Now we take this to the other side. It will be 10 log 11 d to the power 11.5 here is equal to this value here, 89 minus 31.67 plus 161. And let's see this value how much. It is 89 minus 31.67 31.67 plus 161.4 equal, here it is 218.73. Divide this by 115, because this is multiplied by 10. Divide by 115 equal, and now 10x, you will get the answer here. It is 79.8 meter. So the final answer is 79.8 meter. This is the final answer. Okay. This is the final answer, and we have assumed that the answer is greater than 50 meters. In fact, greater than 50 meters, so our solution is okay. Polarization effects. A cross coupling, when a vertical polarized wave is incident and it is reflected from buildings, scattered and diffracted, there would be a resulting horizontal component, and this is cross polarization. This is the attenuation. In residential area it is lower, and medium it is higher. In urban, because it has more dense buildings and higher buildings, the attenuation is higher. So in urban it is higher, in medium city it is lower, in residential area it is lower, of course. And this is the standard deviation, because the buildings are not the same. So this standard deviation for urban, for medium, for residential. That's all for now. Thank you for listening, and see you in